today we'll be changing gears again this week, and we'll be talking a little bit more about probabilistic models, things that incorporate more probability into the way they make predictions, rather than just say straight up classification of what the students should do. First couple announcements. Homework 4 is released. It's due in a week. It has a coding portion, so when you do the homework, just make sure you write clean code that's readable by the TAs. Feel free to comment. There's also skeleton code for loading the data. I know a couple students have problems just getting caught up with how to load data and munch data in Python or MATLAB. So if you want, there's a skeleton code for loading the data available on Moodle in both MATLAB and Python. You don't have to use it. You can use your own data loading sort of script. Doesn't matter. But if you do want to use it, it's available for you. And I think it's pretty clean.
Thanks, Yiso.
You're welcome, noob. Okay, so today we'll be talking about probabilistic models. And the most basic one that sees use in regular practice is naive Bayes. And we'll talk about how to even use probabilistic models like naive Bayes to do things like training, estimation, sampling, inference, and stuff like that. At the end of this lecture, I'll give a brief overview of advanced probabilistic models, one of which is hidden Markov models, which will be the topic of Thursday's lecture. All right, so generative probabilistic models. A generative probabilistic model models the joint distribution of both the x and the y's. And in fact, to some degree, depending, at least at the highest level of abstraction, a generative model makes no distinction between an input feature and a label you want to predict. It just wants to model the whole distribution of x and y given some training data. Of course, if you know that you want to make predictions on a certain variable y given some other variables x as input, and maybe that's how you want to use the model, then of course, from sort of basic probability, you can apply Bayes' rule to compute the probability of y given some input x. So if you give the model as input some x feature vector, then you want to model, and y is a binary variable, let's say +1 or -1 or something like that, then you could compute the probability of y being +1 or -1 using this equation, which is Bayes' rule. And the standard prediction problem that we've been talking about sort of the last 3 weeks is, choose the prediction that's most likely, right? And so what we call prediction in the last 3 weeks would simply be equivalent to computing this distribution by Bayes' rule and then choosing the y that would maximal p of y given x. Right? And we could also do other things, where we could do more than just do standard prediction using a joint model. We can do things like infer with what's called a marginal distribution. So for example, if I want to just know what the probability of y is, so just average out over all the possible x's that the training this data set provides, I can do it like this. This is a standard probability equivalence. Equation equivalence is that if you went to recitation last Thursday, you should have seen. And so all of these things are possible if you specify the joint distribution, which in some sense captures the most information possible. Here's a very simple example. So x has 3 values, and y has 2 values. So you have a single x that can take on one of 3 values. You have a single y that can take on one of 2 values. And I've just written out the model. So this is the entire model. It's a very simple model. Since p of x, y is a distribution, this column must sum to 1, and hopefully it does. I double checked it, hopefully it does. And then we can ask a question like, okay, given that this is our model, p of x comma y, what is the probability that a random data point from our training set, as summarized by this model, has an x value equal to homework, right? So you could think of this this is a stylized example, but you could think of this as sort of, if I received an email with just a single word in the subject, what is the word, right? But this is obviously a stylized example for simplicity. So we could ask this question. Given our model, what is the probability that any given piece of email or document in our training set has a subject header homework? And the answer is 0.5. And how you get that is you simply sum over, so you have the full joint distribution, you simply sum over all the possible y's while keeping the x fixed. So that's basically 0.05 plus 0.45, right? That keeps. That's these two. This equation, and it gives 0.5. So the probability that any given document, according to our model, the probability that any given document from this distribution has a subject header homework is 50%. So if I would take a random document or email from this data set, there's a 50% chance that it'll have the subject header homework, which is the way it should be at Caltech. Okay, let's ask a different question. What about the probability that given that I have a document with the subject header help, what is the probability that this document is spam, right, according to this model? And we'll talk about how to train these models later on in the lecture, but suppose we've already trained the model, this is exactly what it looks like. What is this probability? Well, we can apply the law of conditional probabilities. P of y given x is equal to the joint probability of p of x comma y divided by p of x. And p of x, of course, is the marginal distribution of summing out over all the possible y's, right? So the answer is 60%, 0.6. So p of x comma y for this specific xy pair is 0.15. And p of x is, let's see, for x equals help, is 0.15 plus 0.1, which is sums to 0.25. So condition on the email subject header being help, there's a 60% probability that the email is spam, according to our model. Okay, I mean, it's a joint distribution. The model itself at this level of abstraction is actually indifferent about what is the label and what is the input feature, right? You could actually reverse the question, right? The model itself is actually completely symmetric, at least this simple version of the model. So we can say, okay, what if we just reverse our interpretation of which one's the label and which one's the feature? And what is the probability that if an email is not spam, its subject header is help? And you can do the same, sort of, basically the same idea. You just reverse all the definitions. You compute use the law of conditional probabilities to know that this formula is equal to this. This is let's see, how not 0.1, and then the y you marginalize over all the possible x's. So you look at all the probability of every entry in this table with y equals to not and x equals to anything, everything. And that sums to 0.6, if I did my math right. And so the probability is about 17%. Any questions? Okay, so this is a nice flexible model. How do we train it? And so here's how we think about training these types of generative models. Generative models, their goal is to learn the entire distribution p of x comma y. From that, you could reason about whatever type of probabilistic query you want, including the standard one of probability of y given x. So if our goal is to learn all of x and y, a joint distribution of all of x and y, what should be the objective function? Any guesses? So the objective function is maximum likelihood. So we've seen this interpretation for logistic regression, where minimizing the log loss in logistic regression is equal to maximizing the likelihood under a certain modeling assumption, which is a logistic regression modeling assumption. It turns out that the principle of maximum likelihood can be applied more broadly. You just define a different model, and you just maximize the likelihood of your model on your training data. Okay? And so this term right here is the principle of maximum likelihood, where S is your training set. And this diverges from the definition of logistic regression because logistic regression only cares about the probability of y given x. It doesn't care about the joint distribution. And that'll lead to this term, which is mathematical equivalent in terms of the minimizer, or the optimal solution, will lead to the log loss formulation if this is p of y given x. But we are actually interested in modeling the joint distribution, so we just simply maximize p of x comma y instead of p of y given x. Okay. So we just simply apply the principle of maximum likelihood to try to fit a different probability distribution to our training data. And it turns out, for this type of model, that the solution, and I'll show you the derivation in a couple slides, is just based on frequency counts in the training data. And in this particular case, in this simple example, there are exactly 6 parameters. If I exhaustively enumerate sort of all the XY combinations, there are exactly 6 parameters. So the goal of this learning problem is to learn 6 parameters. So the interpretation of sort of these probabilistic models is, given some model structure that I want to learn, find the parameterization that best explains the data. If my model structure is I only care about P of y given x, which is logistic regression, then finding the model, the parameterization that best fits the data leads to minimizing log loss. So it's sort of that's the equivalence. If my model structure is I want to model the joint distribution, then I get something that gives something a little bit different that I'll show you in the next slide. But is there any sort of high-level questions about the principal maximum likelihood? Yeah.
So it seems like you kind of assume that you have sufficient samples to at least have a few counts that you would care about. Like if you had a sparse data set.
Right. So I'll talk about regularization. So that's overfit. That's basically the issue of overfitting, and regularization is one way to deal with that. I'll talk about that a few slides later. Did you have
What were the 6 parameters?
Basically, this model, the way I described this very simple model, there's in this universe, x, there's a single x and a single y for any training example. And x can take on 3 values and y can take on 2 values. So the Cartesian product of that is 6.
Oh.
And so there's just exactly these 6 numbers that I need to learn. The model is entirely specified by these 6 numbers, and that's what I need to learn from training. We'll get into more complicated models later, but sort of for now, it's just that, yeah.
So, a general question, how do you choose a parameterized model?
A parameter, so,
Yeah. You first need to choose the model space.
yes, you need to choose what the representation of x that you're measuring is, right? So for example, here, again, this is a very stylized, simplified example. You can imagine there's other data in each document. I'm just throwing them away, right? I'm just not measuring it, right? I'm just measuring the one-word one-word subject and then some label that an annotator gave. So one way to answer your question is you have to choose what you measure, what you record, and then you have to choose if there's additional structure to this model. This model is unstructured in the sense that it has one parameter for every Cartesian product of x, y. And so for really complicated models, you have to impose more structure, otherwise there's an exponential blowup, which we'll talk about later on in this lecture. Yeah?
So something I'm a little confused about. So you said that if we just looked at maximum likelihood of P of y given x, we'd be doing logistic regression.
Yes, it's mathematically equivalent. Yeah.
Okay. So if we did this, if we found the joint distribution, and then we asked what is P y given x, would it agree with what we find?
No, not necessarily.
Okay, so you could end up with 2 different models.
Yes. So logistic regression. So I should be a little bit more clear. Logistic regression not only trying to fit P of y given x, it's fitting P of y given x as a linear model in an exponentiated space.
Okay.
Here I don't make a linearity assumption. I just do a full Cartesian product.
Gotcha. Okay.
Right. And so if there's in logistic regression, in linear logistic regression, there's other types of logistic regression. You maximize P of y given x given the linear and the exponent assumption. So you make one further assumption. But in more generic logistic regression, then yes, you might get something equivalent if you have enough data.
So in fact, this linearity is the structure you mentioned just now.
Yes, it's a limit. It's a structure in the sense that it restricts the kind of models you can learn. Linearity is certainly one. Yeah.
So what is the argument for maximizing over here? Is there should there be like a theta in the xi or what?
Shouldn't there be I'm sorry, what
A
theta?
theta, just like
A parameter vector?
Yeah, I mean.
Yeah. So right. I guess the parameter vector is implicit. I just didn't include it. So you're sure, like you are maximizing some parameterization of this probability distribution implicitly. Yeah. I just didn't include it because it just gets messy. Okay, so I've mentioned that it's just the solution for this particular type of model. It turns out to be frequency counts. And here's the derivation. Suppose I just reparameterize the probability. The probability of P of x given y is this, right? So what this is some parameter for each Cartesian product for each cell, and then I normalize so that it's a probability distribution, right? Normalized by the sum of all possible xy pairs. Then this minimization problem, which is mathematically equivalent to this one, is equal to this. If I take the log of if I take the log of this term, it becomes like this. Excuse me, the negative log. If I take the gradient of this with respect to a single, entry, which is a single xy pair, I get that this term is 0 unless xi, yi matches xy. So this term, if I take the gradient of this, is 1 over wxy times the number of times that this matches this in the training set. And this term is simply the number of data points in the training set divided by 1 over this. It's just simple calculus. Set this gradient equal to 0, which is the optimal solution, and I get this, rearrange terms, and I get this, right? So remember that this is exactly this. So I'm just doing a reparameterization, so these two terms are equivalent, right? And so now I see that the optimal solution to this minimization problem for every xy, so for every parameter in my unstructured model, which is every cell in this Cartesian product of probabilities, the optimal solution is simply, of the maximum likelihood estimate, is simply the counts, right? The number of times that this xy pair, so this subject labeled pair, happens in the training data, divided by the total number of examples in my training data. And in general, if you're being completely unstructured, these are the types of sort of maximum likelihood estimates you get, which is, I assume no structure, everything's sort of in its own. I mean, estimate each individual parameter in a more or less independent way because there's no structure, and so you're just the maximum likelihood estimate is just sort of some sort of frequency count. There was a question asked. Was it Noah who asked it? About regularization, and yeah, so obviously, if this number is highly, in my simple example, there was only 6 xy pair possibilities. Imagine if there was, a million, right? This can give you unstable estimates, right? Especially if an individual xy pair happens very infrequently. So this is of course a problem that's sort of everyone knows about, and so regularization is the way you deal with it, obviously. And so the way that people typically use regularization to deal with this type of issue, the most common thing is to use what's called a pseudo count. And the people who invented this method basically they call it a pseudo count, and it's more or less equivalent to using hallucinating data. Right? We talked about hallucinating data as being equivalent to a regularization for L2 regularization for linear regression a few lectures ago. I won't try to derive the equivalence here. It's a little bit more complicated, but you could use more or less the same approach, right? The same approach, which is I just pretend that I observed some amount of xy pairs, so in my training data, and then the strength of the regularization is lambda, which is a non-negative scalar, and then I divide by adding this lambda as well. So it's like saying in the absence of actually observing actual data, I'm going to pretend I observed lambda data points where p sub xy, a fraction of those lambda data points belong to xy, is of the form x comma 1. And then as I observe more data points, then in the limit of infinite data points, this part of the ratio dominates this part because this part never grows. Right? So this is the standard way to deal with overfitting, unstable estimates, and how to do regularization of these types of models. It's called pseudo counts, basically equivalent to hallucinating data points.
So would this work only if x is discrete?
No, you can also do it when x is continuous, but then you have to introduce some more parameters. So for example, if x is continuous, you assume it follows a Gaussian distribution. You could, and then if you add a data point, you could update the Gaussian posterior, right? Yeah, in general, you can always hallucinate data points, right? That's a form of regularization. Yeah.
What's PXY?
It's just it's a user specified, just my prior regular assumption.
Okay, so you have two parameters, the lambda and PXY.
Typically PXY is uniform, just uniform distribution.
Oh, it's their prior.
Yeah. It's typically if you just want stable estimates, you don't know anything about your data. The best you can do is uniform. So this would be, in our case, PXY would be 1/6 for all possible XY.
Is there anything out of just assuming xy are independent, so just px times py as a prior as opposed to doing uniform? Or is that not really useful?
So if you assume that Px is uniform as 1/3 and Py is uniform as 1/2, then all of them are going to be 1/6 anyways if you do a product.
Okay, yeah,
Okay, so all the methods that we've talked about thus far in the previous 3 weeks are called discriminative models. And what I described is called a generative model. And the basic difference is that a generative model models both y and x, and discriminative models model y given x. There are versions of discriminative models that are probabilistic, like logistic regression. Many discriminative models are not even probabilistic. They don't even have a probabilistic interpretation. Generative models, by definition, have a probabilistic interpretation because they model the joint distribution of p of x comma y, and from which you can sort of conduct any type of queries by marginalizing out or taking slices of this probability distribution to answer various questions. So what are some of the benefits and drawbacks of generative models as compared to the discriminative models that we've been thinking about in the past 3 weeks? So here's some basic differences. In this example, this simple example, a generative model, it keeps 6 parameters, right? A discriminative model only keeps 3, right? Because the discriminative model only cares about probably y given x. It only needs to keep 3 parameters, but it has fewer parameters. Typically, that means that it's going to be more stable in terms of learning. A generative model, you can sample from p of x comma y. So I can say, if this is the actual model that this really describes how this data is generated, so this is my model of the test distribution, if you will, I can actually draw samples from it, right? To see if it looks like my training set. In discriminative, even if it's a probabilistic discriminative model, you can only sample p of y given x. You cannot sample from the joint distribution. Because you model the joint distribution, typically the standard prediction task, you have to do it in an indirect way, such as via Bayes' rule. Whereas the discriminative models directly model the discriminative task, so they can be more accurate. One of the advantages of using Bayes' rule in a generative model, of course, is you have missing data in your input x features. You can actually marginalize those out, and I'll show you an example of that later on in this lecture. Whereas you cannot naturally do that in a discriminative model. So discriminative models, in the sort of perfect case where you only care in the case which is often the most common case in practice, but still just a special case of there's some y I care about predicting. That's the only thing I care about predicting, modeling, given the input x. There are no missing values, so I always observe the full x in my training set and at test time. I just want to make the best possible prediction on p of y given x as possible. If that is your goal, you should always use a discriminative model. You should never try a generative model because the generative models use up more model capacity to model things that only get indirectly combined to compute this value. Therefore, it's less reliable given finite data. So, for example, if naively, if these numbers are really small, like super small, like I compute this and I compute this and then I underflow and I take the ratio and I get like not a number, right? In the extreme case. Furthermore, the training objective, right, of generative models do not maximize predictive accuracy. They maximize the likelihood of your generative model explaining the data, which is not the likelihood of you making good predictions of y given x. So, of course, because generative models are joint models, they're a model, they're a summary of the test distribution, right? And so, once you fit the parameters of your generative model to your training set, you can actually draw samples from it, right? And see if they mimic your training set. And so here's how you can draw a sample. And drawing samples is fairly straightforward. If you've never drawn a sample like this before, here's how it works. Typically, you sample a random variable using a random number generator, such as uniform between 0 and 1. This is a built-in function in MATLAB or Python. And for this simple case, you take this number and you partition it into segments. And each segment corresponds to predicting one of these 6 cases. So if the random number is less than 0.15, you sample, your test set samples, your model samples this case. If it's not less than 0.15, it's between these two numbers, then it's less than 0.25, which is in this region. You sample this case, and so on and so forth. perhaps the most interesting case is generative models can tolerate missing values. Right? At least the most interesting case we've talked about thus far. So what happens if you're missing a feature at runtime? Right? At test time, you have this feature vector, and one of the entries is missing. Because you could measure it, it gets corrupted or whatever. It does happen. Logistic regression can't do anything. Right? It only models y condition on all of x. You can use heuristics like plug in a value, but that's not principle, that's just a hack. Generative models says, well, okay, I know the joint distribution. If I don't observe this x, I can just marginalize it out. And so we'll see this specifically for naive Bayes, as when I talk about a naive Bayes in a few slides. But yeah, discriminative models cannot naturally tolerate missing values. Many people in the machine learning community think generative models are more elegant, right? They tell a complete story about the data. Right? If you have a good generative model of your data, you could use it to gain a lot of insight from your data because it's a compact representation, and you could ask any kind of query you want. And typically in machine learning lingo, this type of a query is computing some sort of slice of the joint distribution and seeing what that slice looks like. It's also useful if we can't decide a priori what the prediction task is. Here's the data. I'm actually not sure what is the y that I care about a priori. So I'll just build a whole joint generative model and hope that I've estimated the model good enough. And then I can ask any p of y given x for any definition, for treating any variable as the y using Bayes' rule. Yeah?
What do you mean by tell complete story? What do you mean by complete story?
So basically, the only thing I mean is that it specifies a full model of the test distribution.
For the distribution, if I have x, I can predict what it y.
But that only if you have the x, right? That's only half the story, if you will. Given an x, I can tell you what the distribution of y is for logistic regression. If you don't give me an x, I can't tell you anything. In some sense, that's half the story, right? Any other questions?
So do you agree, Simon, that generative models are more elegant?
They can be. I think it's task specific. If your data has a lot of missing values, I just don't know what else you can do. But if your data, if there's no missing values and you're just trying to predict the y, and you know what the y is, there's no reason to use the generative model. So there is no single viewpoint that dominates all other viewpoints because this is all subject to different use cases. But I would say that sometimes, yes. Cop-out answer, I know. But I believe it's the most useful answer.
But if we only have a very small portion of data which is missing, then if you use generative model, then you get to a very unstable method. So
Why do you say that it's unstable?
Because it has much more parameters.
Right, so you need a lot of data, or you need to impose more structure, one or the other.
So can the discriminative model do something on missing data, but the missing data is sparse or very small portion of the data?
So what some people do is they impute the missing value as the median of the training set.
Yeah.
I mean, that works okay sometimes, and it fails catastrophically other times. As you might imagine, like a decision tree, if there's a missing value and I just replace the missing value with the median from the training set, it can be quite bad. Right? Like it could split in a way, it could cut, like at runtime, this test example with the missing value, it'll just split, it'll just traverse down a completely wrong branch of the tree. So there is no sort of nice sort of systematic way to deal with missing values in a pure discriminative model. There are people who do like discriminative model. So there are ways to build a discriminative model component from a generative model. Like you can impose structure. For example, you could do Bayesian logistic regression. where you model the fact that you might be missing feature values with some probability. And then you can model a logistic regression condition on that. But I won't get to that sort of in this lecture, but there are ways you can sort of do that. Yeah?
So how do you know that the distribution of your data before your training?
So you make an assumption about the structure of your distribution, and then that introduces a number of parameters, and then you fit those parameters using maximum likelihood. In this particular example, I imposed no structure,
Yeah.
right? So it's unstructured, so I have to compute one parameter for every Cartesian product of these values. I will show you another structure called naive Bayes, which is probably the most common one people use in practice. Yeah. So let's say we want to model a vector of x instead of just a single x, right? So we have a single y, let's say it's a binary variable, and we have a vector of dx's. So bag of words representation. And then what is this considered the case where each entry in this feature vector is binary, so 1 or 0 or something like that, right? So for example, you can interpret it as the presence or the absence of a word in a document. And again, we want to model the joint distribution. So given a training set, we want to sort of build a distribution subject to some structural assumptions of the model that mimics this, that explains or mimics this training set as well as possible. So here's a simple example with a feature vector of length 2. Given a piece of email, whether or not the piece of email contains the subject header contains the word winner, or contains the word homework, or both, or neither, right? And again, I'm using the completely unstructured case where I have one parameter for every Cartesian product entry of all possibilities, right? And so now I have, so there's 8 possibilities, right? I guess I was going to ask what's wrong with this approach. Many people already jumped the gun. What's wrong with this approach is that the model complexity in the unstructured case is exponential with respect to the length of x. Right? If you model d features, it's exponential in d. Right? So if there were 3 instead of 2, you'd have 16. If there were 4, you'd have 32, and so on and so forth. And this is for binary features. So to deal with this, the simplest way to deal with this in the literature is to use an assumption called, use the naive Bayes model, which makes the following assumptions. The assumptions is as follows. The naive Bayes formulation posits that the structure of this joint distribution follows this multiplicative decomposition. And you could sort of visualize it using what's called a graphical model diagram. And the basic idea is that you have some probability distribution over P of y, and then you can model the conditional probability of P of x given y. Furthermore, the conditional probability of P of x given y factorizes into an independent product of each individual feature. And this is called the conditional independence assumption, right? Given the y, the x's are conditionally independent of each other. And this is the key assumption that allows to have a tractable model in terms of the number of parameters. And this is called the naive independence assumption. That every feature in the feature vector is independent, has an independent distribution condition on the label. So this is the only things we need to keep track of.